Hi everybody, Physics Ninja here. Today I want to look at the potential V that's created from a charged disk. So here I have a disk and I've placed the disk in the XY plane. What I'm going to do to that disk is I'm going to give it a uniform charge distribution. So that's the sigma over here. And again, this is going to be a constant charge distribution. What we want to do now is I want to go above this disk a certain distance. In this case, it's going to be denoted by the letter Z. And what I want to do is I want to calculate what is the potential V right here at this point. Right? And what happens then in the limit, what happens if that point is very, very far away from the disk? What happens if it's very close to the disk? What else can we calculate? If I know the potential as a function of that letter Z, I can also calculate what the electric field is. So what is the field when I'm close to this plate or if I'm very, very far away from that plate? So it's kind of a nice problem. It's going to involve some integration because I have a uniform charge distribution. So we're going to start by setting that up and then do all the rest of the calculations. All right, again, thanks for watching. If you like the video, give it a thumbs up. If you like what I'm doing on my channel, consider subscribing. And always, if you have questions, leave them in the comments section. I will get back to you. All right, let's get started. Okay, so to get started, what I'm first going to do is I'm going to consider a tiny little patch right here. And this little patch here has a charge, which I'm going to denote as dq, some infinitesimal amount of charge. And I want to evaluate its contribution to the electrical potential at this point here, point P, which is a height Z above this disk. This disk lies in the XY plane. Let's go ahead and just write this as that distance over here. Now we have to define one more thing. The distance now from the origin all the way to where this charge is, let's call that r prime. And now you should be able to write that the distance from this little charge all the way to that point, this is just using Pythagorean. Nothing too complicated here. It's r prime squared and plus z squared. All right. Now we should be able to write an expression now for the potential produced by this little bit of charge. And I call that an infinitesimal potential because it's only the contribution from this little charge. At the end, you'll have to integrate in order to get the total contribution. So again, this is simply dq divided by 4 pi epsilon 0. And the distance, it's always the distance away from the charge to the point where I'm evaluating in that. So that distance is what we just obtained. Oops, let's get rid of that. This is r prime squared. And again, plus z squared. All right, so that's it. It looks like that's it. The only thing I have to do now is I have to add all the contributions. So we have to do one more step here. What is this little element of charge? Well, this little element of charge is going to be my charge density multiplied by the area. So let's take this equation one step further. This is my charge density. And multiplied by the area, call it dA. And again, the bottom now just stays the exact same, 4 pi epsilon 0. And again, square root of the rest of this term, r prime squared plus z squared. Okay, to get the total potential, which is really what I'm after, to get the total potential, what you have to do now is we have to integrate. And we're going to have to integrate the expressions like this in order to add up all the contributions to get the total potential. And that here is only going to be a function of z for this particular problem. Okay, so let's evaluate this integral. We're working in cylindrical coordinate systems, so the potential as a function of v. Let's take out all the constant terms, so you should have a charge density, which pops out. The other terms that pop out are going to be this 4 pi, the epsilon 0, and now I could write out the integral. Now there's two integrals because I'm integrating over the total area of this disk. And in cylindrical coordinates, the integral goes from 0 to 2 pi. That's for the angle theta. And I also want to integrate over the total radius. So that'll go from 0 all the way to uppercase R. That's the radius of this disk. And that's it. Now here I'm going to replace this little element of area. Again, the little element of area for cylindrical coordinates can always be written as r prime, dr prime. And again, I've already got the d theta here. Okay, so maybe let me just explicitly write this down here that the area can also be written as dr times r prime and multiplied by d theta. Okay, that's where this whole substitution over here came in. So don't worry about that. And again, at the end, we're still left with this term here in the denominator. In the denominator, I still have this square root term, which is r prime squared and plus z squared. Okay, so this looks like a nasty expression. The first term, however, this is pretty straightforward since there's no other dependence on the angle theta over here. The integral from 0 to 2 pi of d theta simply gives me 2 pi. So let's go ahead and simplify this even more. So we get our charge distribution sigma. We get the 4 pi epsilon 0. This first integral, let's just write as this. This is going to be 2 pi. And now the final integral, we'll go on the next page in just a second here, but this is really at the heart of the problem. It's square root of r prime squared plus z squared. Notice you can cancel out 2 pi. You can cancel out, and you're left with a 2 here at the bottom. Okay, so now let's go on the next page, and I'll show you how to evaluate this second term over here, the second integral over the total radius to get our final expression for the potential. All right, so to evaluate the second term here, what you have to do is you can either look it up in an integral table. This one's actually pretty straightforward. We could do just this substitution. I'm going to do a substitution where I'm going to define u as r prime squared plus z squared. Now, if I make that substitution, that means that the limits now of the integral have to change, right? Instead of going from 0 to r, the limits, the new limits here are going to be, well, the lower limit is you substitute the 0 for the r prime, so you have z squared. And the upper limit is you're going to have uppercase r squared plus z squared. So those are our new limits of integration. The other thing I have to do now is I have to differentiate this. That means that du, and if I differentiate that with respect to r, what you end up getting here, the second term is just acts as a constant because I'm not differentiating with respect to the letter z. And what you're left with here is simply 2 r prime. Now that doesn't quite look like the top term, so we have to just rearrange it a little bit. If you rearrange it a little bit, what you're going to find here is that if I have r prime, dr prime, that should be equal to du over 2. Okay, so now we go ahead and we make the substitution, and this is what we should end up with. That my potential, at least the integral, can be written as the first terms don't change. These are only constant terms. Now I'm changing, I've made a change of variable over here. So what I'm changing now is I'm going to integrate all the way from z squared all the way to r squared plus z squared. Okay, now we make the substitution for all of these terms over here. So the r prime dr prime, well, that gets substituted by this guy right here. So that simply becomes du divided by 2. All right, now here I'm still dividing by the square root of this term. And that one term is pretty easy. So I'm going to have the square root of u. Okay, now this is getting pretty straightforward now. Actually, this integral right here is one, it's pretty straightforward. So let's go on the other page and evaluate this and get to our final expression for the potential. Okay, so this is pretty straightforward at this point. All we have to do is maybe pull out the 2, bring that to the front. And then we're left with a very, very simple integral, but let me just do one intermediate step for you. Over 4 epsilon 0. Again, these are still going to be the same limits. I'm not going to rewrite them over here. And what you're left with here is du divided by square root of u. And that term is pretty straightforward. All right. I always like to write it, I don't know, for me, my personal preference here is just to write it as u to the minus 1/2, right? That's exactly what this term is. And the integral with respect to du. All right, so this, you should be able to just write this down, right? This is kind of a standard function. So we get over 4 epsilon 0. All right, now this guy here is, again, you add 1. So we're going to have u to the, if you add 1 to negative 1/2, you're left with 1/2. And then you also have to divide by that term, by the same term. So we get this. And again, this is evaluated now between the limits of z squared and r squared plus z squared. So all we have to do now is simply substitute those limits into this expression, and we'll have our final expression for the potential. One thing I could simplify over here, this 2 can cancel out. I could take 2 out of there, and I'm left with this. All right, one last step. We get to our final expression. Let's do it. So I'm left with now just substituting those limits. Sigma over 2 epsilon 0 remains the same. Now again, if you substitute r squared plus z squared into here, I'm going to write it in kind of a slightly different form over here. Let's write that 1/2 as a square root. And here I'm left with r squared plus z squared. So it depends on how far away you are, right? That makes sense. And also on the dimensions of the disk. That also makes sense. And don't forget to substitute this lower limit here because we did a change of variable over here. Okay, so we have something like this. The other thing you can do now is, you could simplify this a little bit. If I wanted to factor out a z, I could do that. So let's go ahead here. And that would look like sigma over 2 epsilon 0. Now if you take out a z over here, again, imagine the z is above the disk, or if it's below the disk, you're going to get the same potential, right? It's going to be some positive value of the potential. And you can see that this is always going to be a positive value. Right? There's nothing in this term here, again, assuming that the charge density is positive, but this first term is always going to be bigger than the second term. All right, if I factor out a z, I'm just going to write that as absolute value of z. What you're left with now in the bracket is, again, if you factor out z squared from this square root, you'll end up having absolute value of z over here. So the first term will look like this. Just change the order a little bit. This will be r over z squared. Make sure you can kind of understand that step. And again, this is going to be -1. And you're going to see why in a minute that I kind of like this form over here. All right, so this is the value or a function of the potential as a function of the value z. Okay, I want to examine this equation here on the next page, and we're going to take some limits here. Like what happens if I'm really, really far away from the disk, and how can I use this expression, for example, to calculate the electric field? Okay, but we've done all the work. This is really the final expression. But let's go on the next page just to make sure this expression makes sense physically. All right, so here's our expression that we got. And this is a general expression here. I haven't made any simplifications to this expression. This is just what the math gave us, what the calculus gave us. So it looks like a rather complicated expression. However, now I want to explore a limit. And it's always a good idea to explore limits when you get to algebraic expressions like this. So the first one is, what happens now if I'm really, really far away, right? And that means what happens if z is much, much bigger than the radius? Think about it. So you have a disk in front of you and you go to a distance that's really, really far away. First of all, the potential should be small, and we're going to find that. However, how does the potential vary if you're really, really far away from a disk? Well, if you're really, really far away from something that looks like this, it probably looks like a point. So our result here, which doesn't look like a point charge, it should reduce to that of the point charge when I'm far away from it. So let's go ahead and make this verification. So when you're far away, what I'm going to do here is first look at this term. All right. If z is bigger than r, that means that this term over here that's going to end up getting squared is going to be a small term. Okay? So let's first look at what that term looks like. In this limit, this term over here, which is square root of 1 plus r over z squared. Let's get rid of this. Don't need that. That there is approximately going to be equal to, let me write it out. There's one extra step first. Some people might not know this, right? This is just using kind of a binomial expansion. Let me just write it as 1 plus r over z. Again, this term here is squared. And this is really to the 1/2, right? And in the limit of z much bigger than r, this here becomes approximately equal to 1 and plus 1/2 r over z squared. Now there's higher order terms, but we're just going to keep those terms. Now if you completely neglected this term, if you say that z is really, really big, well then you might just completely get rid of this one, and then you would have 1 under the square root minus 1, and that would give you 0. Well, that really doesn't give you any functional dependence over here, so we're going to keep these first two terms for this expansion. All right, let's have a look now at what we end up getting. So we get sigma over 2 epsilon 0, absolute value of z, and now this whole term here, now the 1's going to cancel with this. So the 1 here Again, we can write out the whole square bracket, but we have 1 plus 1/2. This is r squared over z squared, and minus 1. Close the bracket. All right, this will cancel with this. Now what you're left with over here is, again, this 2, I can bring it out to the front. So let's write down all the terms over here. So we have our charge density. The charge density here you can really write as the total charge. That total charge of the disk is going to be some value q, and divided by the total radius, the total area of the disk, which is simply pi r squared. Okay, so if we go ahead and do this, let's get rid of the charge density here and write it out as q, and divided by pi r squared. Now this 2 is going to combine with this one right here. That's going to combine to a 4. All right, what else do we have? The other terms here is I have a z up here, and I have z squared over here. So this guy here can cancel with one of those. And you'll notice that the absolute values are also taken care of here. And the last part here is I simply have an r squared that's left over right here. So that term has to stay. And I'm also going to have just one z here in the denominator. Notice the r squareds cancel. And now if you're a little bit careful and we group all the terms together, what you're left with is the total charge of that disk divided by 4 pi. And there's a z here in the denominator. And that there's the potential. And that just looks exactly like the potential produced by a point charge that has a value q. And if I'm a certain distance z away from it. So this here totally checks out, right? That one there makes sense physically. So when you're really, really far away, this whole disk just acts like a point charge. And now you can also calculate the electric field and you'll get to the standard expression. All right, in the second case, what I want to do now is what happens now if I'm really close? If I'm really close to the disk, again, if I look at my general expression, that's okay. And in this limit here, z is going to be much smaller than r. Now I don't want to set z equal to 0. I'm just going to be above it by some small value. So what would that look like? Well, in this case here, if I look at the term in the square root, if z is small, that means that this second term here is going to be pretty big. And it's going to be much bigger than the 1. So in that case here, I can just neglect the 1 term over here. And what you're left with is that my potential is going to look like this. This is z. Okay, now you can cancel out the 1 here. Forget about that term. This second term is much bigger. And it's squared, and if that's under the square root, again, what we're going to be left with here is r over z. And again, minus 1. Again, that's what the square root term simplifies to in the limit that z is much smaller than r. Now, if you carry out this multiplication over here, what you're left with is this term. Again, I'll just multiply through by this absolute value of z. And what you're left with here is r, again, minus z. Actually, does this make sense to you? That's what you have to ask yourself, right? This first term here, what does this first term represent? It's simply a constant term. And that's actually the potential of the disk, right? If I'm right on the disk, and then what does this tell you? The second term over here tells me that it varies linearly with distance from the disk, right? This is a linear term. And does that make sense? Well, think about it. What if now, if you wanted to evaluate what was the electric field? How would I evaluate the electric field if I'm really close to the disk? Right? The electric field you should be able to write as the derivative of the potential with respect to my variable here. No, with respect to dz. All right, if you take the derivative, and let's just assume that here we're above this disk, so you don't have to really worry about the absolute value. And what you end up getting here in this case would be that the electric field, the first term, if you differentiate it with respect to z, you get 0. This negative sign will cancel with this one right here, so you don't have to worry about those. And if you take the derivative of z with respect to z, you're simply going to get 1. And the value of the electric field that you get is going to be sigma divided by 2 epsilon 0. Right? This is the electric field just above the surface of the disk. And that's exactly what you would get if you would use something called Gauss's law. Gauss's law is often used to calculate fields close to objects, and you get the same result. So if we were going to sketch now what this potential looks like, again, these are the results for the two limits. Far away, we have a potential basically due to a point charge, and Q was the total charge of the disk. When you're kind of close to the disk, if you're really close to something, it basically just looks like an infinite flat surface. It's not really infinite in this case. It does have a finite size. So what you have here is a potential that drops linearly with distance away from the disk. Okay, and that also reduces to an electric field that's more or less constant, right? There's very little dependence on the distance if you're close to it for the electric field. Now, if we were going to make a sketch of what V looks like as a function of distance, it would look something like this. So in this first section, it would be linear, and the term here has a negative slope, so it goes down, and then eventually it starts kind of dropping, and when you're far away, again, it looks like 1 over z. 1 over z down in this area right here when you're far away from it. And when you're close to it here, it's linear. And the dependence is basically minus, right, some negative slope because it's dropping. And the value right over here, again, this I can calculate. That is simply this first term over here when z equals to 0. So the value right here is some constant value, Vc. This is basically what Vc is. All right, so that's what the potential looks like for a finite-sized disk as a function of distance from that disk. And again, here I'm just doing the calculation when I'm on the axis, which is the easiest case. All right, hopefully you found this video useful. Thanks for watching.